So I want to start by thanking the PyTexas organizers. I've been coming to PyTexas since 2019. It's my favorite regional conference in this country. Very excited to be back, very excited to be speaking. Also, thanks everybody for coming out to this talk. It's a little bit of a niche topic, but it's something I'm very passionate about, and I hope you learn something about healthcare in this country. So my name is Ali Sivji. You can find me on Twitter. I am at Caius Sivjus. I live on the south side of Chicago, and I work at an early stage healthcare startup called Jasper Health. Jasper is building a patient management solution for cancer patients, and we're focused primarily on psychosocial care. I love working in the healthcare technology space. It's very mission driven, and I'm able to use my technical skills to make a difference, hopefully a positive difference in somebody's life, and I absolutely love that. I also help organize the Chicago Python users group. We call ourselves Chippy. Chippy is one of the largest Python communities in the world. We have over 6,000 members. We're back to meeting in person, so I'd like to you all, thank you. So if you're ever in Chicago, I invite you to come out to a Chippy event, and if you can't make our event, check out our website. We are live streaming all of our talks. So this talk is titled, Unlocking the Power of Health Data. Let's start talking about why does this matter? Say that you're sick, really sick. No, I mean, you're really sick. You have a chronic condition like heart disease, diabetes, or cancer, which is the condition that the company I work for focuses on. On top of dealing with the realities of your life-changing illness, you have to deal with the US healthcare system. And if you have a serious illness, it's not just gonna be dealing with one hospital, it's gonna be dealing with multiple hospitals, with a large care team of doctors, nurses, specialists, and they're all trying to work together to provide the best care they can with the information they have available to them. And this is important. When managing complex chronic conditions, your care team has to coordinate your care to ensure that you're not prescribed medications or treatments that have negative interactions or that result in adverse effects. But if your care team isn't at the same hospital, or let alone the same city or the same state, care coordination becomes a huge problem. And this is fairly common. If you live in a small town in the middle of the country and you get diagnosed with cancer, you probably don't have access to the world-class oncologists. You might have to drive a few hours away to the largest city or fly across the country to see a specialist that knows about your specific form of cancer. And if you've ever spent any time dealing with the US healthcare system, first of all, I'm sorry, you really know how fragmented and just a giant mess. We have independent hospitals, large healthcare system, urgent care clinics, physician groups, outpatient surgical centers. From a patient's perspective, it's a giant nightmare. And from a technology perspective, it's an even bigger nightmare, as none of the underlying software systems in each of these hospitals are able to communicate with each other directly. Seriously, if you refer to one from your primary care physician to a specialist down the road at a different health center, you might be given a photocopy of your records so you can take it along with them, so you can take it along with yourselves to show your specialist. Or if you're really lucky, your hospital might be able to fax or email your records to another hospital. I am being slightly facetious here, but really we're not that far removed from the days where email and faxes were the only ways of exchanging health data for care coordination. So going back to the fragmented healthcare system, each of these healthcare organizations, it has its own silo of healthcare data that it can access, but that nobody else can. And this is where interoperability comes into play. Interoperability refers to the ability for computer systems and software to exchange information and use it in a meaningful way. And when we have interoperability in healthcare, systems can talk to each other to increase care coordination and improve patient outcomes. Now that we know the benefits of having a more connected healthcare system, how do we get there? To understand that, you need a little bit of historical context. Electronic health records, or EHRs, are a digital form of a patient's medical record. EHR contains information such as a patient's medical history, all their diagnoses, medications, treatment plans, immunizations, lab results, images, what have you. The first EHR was created by the Mayo Clinic in the 1960s, but for a lot of time since then, there was really a low adoption rate of healthcare technology in this country. In 2008, only 10% of hospitals implemented an EHR. And even though EHR adoption was not that widespread, people still saw the need for having systems that can talk to each other. Health Level 7 International, or HL7, was formed in 1987, and they made the first attempt at creating a common data interface standard for the rapidly growing EHR and health information technology market. HL7 V1 and HL7 V2 were the first attempts at interoperability standards, but these standards, they just defined a message format, and this unfortunately meant that we had interoperability at a syntactic level, not at a semantic level. And as a result, every single integration we had to build, it had to be configured separately. So this is an example of HL7 V2 message. So you can see that it has a format that defines separators as well as escape characters. It defines the different segments of this message. And then for each field in the message, it contains a data element. But what does this data field represent? Depending on the integration, each field can represent different types of data. And this is the main problem with building an interoperable solution that only works at a syntactic level. Every time we have to integrate with a new system, it means we have to create a brand new integration. And this is really not that scalable, especially with how fragmented this country's healthcare system is. So let's fast forward to 2009. As part of the American Recovery and Reinvestment Act, President Obama also passed the High-Tech Act, which allocated around $26 billion to expand the use of technology in the healthcare industry. As part of this investment, the government created what they called a meaningful use program. If organizations purchased health IT solutions and they could show that those solutions were improving patient care, engagement, as well as increasing care coordination, they were able to get a larger incentivized payments from the government once they hit those goals outlined in meaningful use. So this really kicked off a huge race where established EHR providers like Epic and upstarts started to build new systems from the ground up. And all of these EHRs, they had to be certified by the government before they could be used for meaningful use reimbursement. Unsurprisingly, this huge investment by the federal government increased EHR adoption across the country. And so this is a chart of EHR adoption from 2008 onwards. The blue line is the line for hospital adoption. As I mentioned, in 2008, it was only 10%. And then by 2014, it was almost 100%, so a huge increase. But increasing EHR adoption is great. It's a huge win for healthcare organizations, but does it really mean better outcomes? At this stage, it just means that we have a lot more systems that need to talk to each other. So what's going to go on? What's been happening in the interoperability world while all these healthcare organizations were adopting EHRs? So as part of the EHR certification process, vendors were required to build solutions to share medical information from one system to another. The HL7 organization released a new standard of their interoperability called HL7 V3. And unlike the previous two versions, this version attempted to offer both syntactic as well as semantic interoperability. And this is a minimal example of the HL7 V3 document. This document, which is now in XML format, uses XML tags as well as attributes to annotate different data elements. And this is what semantic interoperability is. Just by looking at that document, we're able to see what the different data element fields represent. HL7 V3 is also known as Clinical Document Architecture, or CDA. And in order to generate a CDA document, what we need to do is, first of all, we need to collect all the different types of resources that we want to include in the doc. So we want to share things like medication information, clinical notes, lab results, whatever have you. Then we're going to need to format all of this data in the format specified by the CDA specification. And then we're going to have to export all of this as an XML document. And as somebody that's read the CDA specification and I've written up a document generator, this process is not really that much fun. You really have to do a lot of work to take data from a format that's being stored into a format that we use for content delivery. And I'm going to admit that this is a step in the right direction. Like, we have semantic interoperability, that's great, but there's still a lot of issues. The world's changed quite a bit since 2005, right? Like, why are we being forced to use XML, where JSON is the most popular format when we're passing messages back and forth? And then the whole point of collecting all of these different resources to generate a document, it feels a little archaic. Each of these underlying pieces of data, it's a resource. Why can't we expose these resources directly and use HTTP to operate on each of these resource types? There's got to be a better way of exchanging information. And this is what led to the creation of HL7 FHIR. FHIR, it's pronounced FHIR. FHIR stands for Fast Healthcare Interoperability Resources. It's a set of healthcare-specific resource types that are defined using a set of attributes that define the data contained in it. I like to think of each FHIR resource specification as a schema. And FHIR data, it can be exchanged as JSON, XML, or RDF/turtle format, but by far the most popular format is JSON. And most importantly, we can interact with each of these FHIR resource types using HTTP verbs. And I think the easiest way to understand FHIR is with an example. So this is a minimum JSON payload for a patient. And so it's a JSON blob. It's something that we've all seen before. Notice that each FHIR payload has a resource type called, has an attribute called resource type. And here the value for that is patient, which makes sense. And this resource has some other attributes like name, gender, birth date, address. And each of these attributes in the JSON payload, it describes the data that it holds. So FHIR is both syntactic as well as semantic interoperability. I think it's better to actually go to the FHIR documentation page to actually see what this looks like. So I'm just going to do that on the screen. So this is the page for the, out of the HL7 documentation for FHIR. Let me just pull up the right one. So at the top, you can see that it is the resource type patient. The thing that you should be aware of is scope and usage. So each of these FHIR resource types, it has this section, and it tells you how this FHIR resource can be used. So the patient resource specifically says that it covers data about patients and animals involved in a wide range of health-related activity. So FHIR is not just for humans, it's also for our animal friends. And if we keep scrolling down, the main meat of this page is the resource content section. And here you can see that we have a patient. We have all of these attributes along with their cardinality, the type of attribute it is, along with a short description. So just going through this really quickly, we have an identifier. Is the patient active? We have their name. So let me just click into human name. And so for name, we can say, is it their official name, their maiden name, their nickname? We can include their period if you get a name change of when your name was a certain one until you changed it. All that information is available. There's also a telecom attribute, and this is a contact point. And so this could be email, a phone number, SMS. You can also specify what your preference is for being reached at. So you can rank all your contact points this way. What else? And so we also have things like gender, birth date, deceased date, address, marital status. You can include a photo of the patient. We have a field for contact to include your emergency contact. And if we keep scrolling down, there is a section for communication, so you can include your preferred language for that. If you keep scrolling down further, it's just going to be additional information specifically about this resource type. So if you ever need to do anything with FHIR patient resources, you can keep scrolling and understand exactly how it is used. Patient, it's one of the primary FHIR type resources, and so it has a lot of information about how patients are linked, because we have things like patient information in multiple systems. So you might have a master patient index, and you can use this to figure out how to set that up. So going back to the top, there's also a section for examples. And here is just a set of examples of of a specific patient. So just digging into this, you can see it's just JSON with all the fields that we just talked about. I actually use these kind of resources to come up with test cases when I'm first interacting with a resource I haven't dealt with before. Okay, so the next thing I'm going to show is, so I just talked about patient. So patient is one resource. In FHIR R5, there's 157 resources that were released. And so I'm not going to go over all of them. That would take way too long. I honestly have not even used like half of these, but the main ones that really matter are, we have bundle on the right here. Bundle represents a set of FHIR resources. You can have one or more FHIR resources in a bundle, and that's a resource itself. For individuals, we have patient, we have practitioner. Practitioner represents a nurse, a specialist, or a doctor that you've interacted with. There's organization, which could be the place where that interaction happened. And on the right, we have encounter. Encounter represents that interaction itself. So it's going to hold links to the patient as well as the practitioner. And so it's more of a data holding type of resource versus containing that much information itself. Where I spend the majority of my time is in the clinical section. So this represents a lot of the clinical types of flows that happen in a healthcare encounter. So you have things like, you can track your allergies, your conditions. So if you go to the doctor, you say a problem statement, we can put it right in here. It also has things like observation, which represents different lab results that you get back. There's also a few for medication. The one that says medication is literally the medication itself, along with its RX norm number, which is just a standardized number that represents different types of medications. And then medication statement's a big one that represents a patient taking some medication for some period of time. There's also things for finances. So if you have insurance, you could represent it with the coverage resource. There's also things about like claims benefits and other things. I don't really deal that much with like healthcare claims, but all of this information is available. And there's also some things about specialized resources related to public health research, evidence-based medicine, and a lot of the things that we have to do in healthcare is report back to the government how things are done so we can get more reimbursement. They call that value-based care. And so there are some resources for that value type, for that type. So now that we have an idea of what the FHIR data model looks like, let's shift our focus to the FHIR server. A FHIR server is an application that implements the FHIR standard. FHIR servers enable us to store and manage healthcare data in a standardized format. And then the server exposes these resources as RESTful web services that clients can interact with standard HTTP methods. There are many different types of FHIR server implementations. There are a few open source versions, as well as versions offered by the cloud providers as managed services. The company that I work for uses Spark FHIR for local development and testing, and we use GCP's Healthcare API for staging UAT and production environment. For what it's worth, GCP has the most mature healthcare cloud, so if you're thinking about starting a product, I would really recommend looking at the GCP cloud. So that's a lot of theory. Talk is cheap. Let's start looking at some code. So I'm going to open up my IDE. Give me 1 second. And so the first thing is I created a Docker Compose that brings up a containerized FHIR server. So just going through this really quickly, I have the Spark FHIR server. The one thing I will call out is I had to create a custom image to support an ARM chip because I'm on the new Mac with the Mac chips, with the ARM chips. If you want to use the x86 architecture, you can just uncomment that top line and comment this line. And there's also a MongoDB behind the scenes, like not very like surprising. Like a lot of this is JSON blobs stored as Mongo. You don't really have to worry too much about it. The FHIR server takes care of it behind the scenes. And so here is just some sample code that helps you interact with a FHIR server. And so I'm going to import requests, set my session. Let's try to do things properly. Set some headers. Just make sure that we are using the application FHIR plus JSON type, just because it helps out the server a little bit there. The next thing I'm going to do is I'm going to create a patient. So this patient has the patient resource type. They have an ID. This is the ID in my system. They have a name, so last name, first name. They have a gender, birth date, and an address. I'm going to go out and put this resource onto our FHIR server, and then I should get back a 201 just to make sure that it was created. And then I'm also going to create a second patient, and this patient is going to have the same information except they're going to have a different ID, a different first name, and a different birthday and gender. I'm also going to put this resource onto my FHIR server, and then I should be getting back at 201. So let me just go ahead and run that. All right, so we can go. I'm just going to open up IPython. Wait, so now I'm going to the FHIR server, uploading those two documents that we talked about. I did not start my FHIR server. Let's do that first. So I'm going to do a make up that just does a Docker compose up. I like make files quite a bit. And then go back here. It takes a little bit of time for the first few resources just to like warm up the server is what I like to think. I have honestly no idea why it takes this long. Okay, so it's good to go. So let's see if those results are there. It's hard to see here. So I'm just going to hit the resource. It's very HTTP-like, or very RESTful, I should say. F is URL / patient / that's going to be patients 1 ID. So here I'm just making an HTTP GET to that patient resource, very RESTful. So I got a 200, that's what I wanted. And now you can see that's the resource I uploaded. It makes sense. Let's just make sure patient 2 also works. And we can see patient 2, and they have a different first name. So all of this information is available through our FHIR server. And so behind the scenes, it's being stored in a database. And since this is in a database and we have access to REST, we should be able to do some sort of searches so we can find multiple patients, maybe meeting some condition. And here we'll just say we're searching people by their last name. So let's just go ahead and do that. And for this, we're going to use a query parameter. So it's going to be a question mark, family _ name equals bhan, right there. And let's look at the JSON that comes back from this. So this one is a little bit more complicated since we did do a search. So notice at the top, it's a resource type of bundle. As I mentioned, bundle is a FHIR type that holds multiple FHIR resources. We can see here that the type is a search set, and we got 2 results back, which makes sense. These people had the same last name. We search for that last name. We get those 2 back. And then going into our entries, that's where the FHIR resources are going to be stored. So we have a list of entries. So there's 2 entries, unsurprisingly. The first element is, this is the URL where we can reach it, and this is the resource. So we can see that it is one of the people that we uploaded, and then the second resource is the second person we uploaded. So it pretty much works as expected. But the thing is, like, we're just pulling data from a server. How do we know that this corresponds to, like, this meets the FHIR specification? We need to do some data validation. And for the next example, I'm going to be using a library called FHIR.resources, which is built on top of Pydantic. And with that, when we get data back, we can validate it and make sure it meets the FHIR standards before we use it in our downstream processes. And so you can see here that we're importing from this library called FHIR.resources.bundle, and we're importing the type of bundle. And it's like before, just setting up my request. This time when I do a get on that query parameter, instead of just like looking at the JSON or dealing with the raw object, I'm going to feed it into the FHIR resources library. So let's run this really quickly. Okay, that ran without a problem. Awesome. So we can take a look at our bundle object. And you can see here that this is a lot of information, but it's pretty much a Python object that has all the information. Instead of coming in through JSON, it's going to be validated through Pydantic and created an object. So just to call that out, we have a date time. So this is like not an ISO 8601 string. It's actually a valid Python date time. So just some notes about what we did. So the first thing we did was we validated FHIR using the FHIR.resources library. As I mentioned, this is built on top of Pydantic's data validation. Right now, Pydantic is purely Python, but with version 2.0 coming out, it's going to have a Rust underneath the hood. So a lot of this validation is going to be a lot faster than it is right now. And just making people aware that FHIR has different versions, just the way that HL7 did. Right now, the most widely used version is FHIR R4. That's the version that's offered by most of the cloud providers for their FHIR servers. FHIR R5 was actually released last week, so this is huge news in my world. Nobody else was probably as excited as I was. But there's a new changes in FHIR which brought in new resources. It also codified a lot of the changes that were made as preliminary changes in R4. And before I go, I do want to say that FHIR is not perfect. Organizations still have to figure out how they want to use FHIR, and not every organization uses FHIR the same way. So you might still need to write up some data mappers to convert from one format to another. But honestly, it's not CDA, so I'm very happy. It's a lot better than what we had. These are all the resources I used coming up with this talk. Thanks for your time. Before I do go, I want to give a shout out to the Chicago Python Users Group. I started learning how to code in 2016, and that organization helped me level up so much. Also want to give a shout out to ChatGPT. Wrote my proposal with ChatGPT. One of my slides was ChatGPT, just one, not all of them, but fantastic tool. Check it out. Thanks again for your time.